So today I want to look at some Lewis structures that don't follow the octet rule. So it's going to involve something like boron, maybe phosphorus and sulfur, in which some of these can have expanded octets, some can have deficient octet, etc. Boron is a classic one. Boron only needs 6 electrons. It's always something that we should write. It's electron deficient and only needs 6 electrons to be satisfied. So let's take a look at this one right. BF3. So again, if you look at the Lewis structure rules, boron will be the central atom since that's the one by itself. And so the way I started off is I like to write boron, the central atom, and then I like to write bonds to all the other atoms. So single bonds. And then I'll put 6 non-bond electrons around each atom. Hydrogen only needs a bond, but everything else is going to need 6 non-bond electrons. So and then what I'm going to do, I'm going to go back and count the number of valence electrons I have to work with. Boron has 3. It's a group 3A. Fluorine has 7. So 24 electrons to work with. Some have to be bonded, some have to be non-bonded. I can only use 24, no more, no less. So far, what I've counted is, well, I've counted 3 bonds. 1, 2, 3. So 3 bonds, 2 electrons in each bond. So 3 times 2 electrons. I'm going to subtract that from the 24. So I'm left with 18 electrons. And then I count the non-bond pair of electrons around each fluorine. 1, 2, 3, 4, there's 6. So 6, 12, 18. So I've used up all my electrons. I don't need any around the central atom. Now fluorine has 8 electrons, and boron has 3 bonds that has 6 electrons, and then we're set. So boron only needs 6 electrons, and then we're set. In terms of the shape, if I have a central atom with just 3 bonds, and again, I'm looking at this, I made a video on this. I'm looking at this sheet right here for molecular geometries. It's going to be a trigonal planar geometry. This is actually going to be non-polar too, might as well, since all these will cancel out. So let's just finish everything. Non-polar molecule. Want to take a look at also now expanded octets. So these ones I do in this video are the ones that don't follow the octet rule. Let's look at PCl5, phosphorus pentachloride. Phosphorus is going to be the one in the middle. Again, the one by itself. That's phosphorus. I'm going to draw bonds to all the chlorines. So. And then I'll draw 6 electrons around each chlorine. That's how you start off. Now I'm going to go back and count how many valence electrons I need to work with. Phosphorus, group 5A needs 5 electrons. Chlorine, or the halogen, group 7A has 7 electrons. I should have said 7. So there's 5 chlorines. Each one has 7 electrons, so these are chlorines. 5 chlorines, each one has 7 valence electrons. That's 35 electrons. So 40 valence electrons I need to use. Got to use 40 exactly, no more, no less. Let's count up how many I've used so far. I got 5 bonds, so I use black here. 1, 2, 3, 4, 5. Each one has 2 electrons, so 5 times 2 electrons. Let's subtract this though. Okay. I'm down to 30 electrons. Each one of these chlorines has 6 electrons. So 1, 2, 3, 4, 5, 6. So that's 6, 12, 18, 24, and 30. So all my electrons are used up. I can't add any more, can't put any more in the central atom, etc. Now each one of these chlorines has 8 electrons, so that's set. So these chlorines are set. Let's look at this phosphorus. This phosphorus has 5 bonds, has 2 electrons. So it has 10 electrons surrounding it. So it's the expanded octet. Phosphorus is going to be a period, I think it's a period of 3. Yeah, it's a period 3 phosphorus. So period 3 through 7, you can use an expanded octet. Because in this case, you can use D electrons. In fact, I think it's period 4, actually. I think that this is actually period 4. Sorry. So phosphorus is actually period. So 4 through 7, you can use those 3D electrons to expand it. So that even though it has 10 electrons, it's satisfied. And so this shape right here, again, if you look at the geometry sheet right here, it has 5 bonds to it. It's trigonal bipyramidal. And actually, since phosphorus is surrounded by 5 of the same atoms, they all cancel out. It's going to be nonpolar. So nonpolar molecules. So all these kind of cancel each other out, basically. If one of these was different, it'd be polar, but since they're all the same, it's going to be nonpolar. I was right the first time. It's period 3 through 7. Sorry about that. And phosphorus is period 3. So sorry about that. So period 3, you can use 3D electrons. Sorry about that mistake. We'll go ahead and do the last one right now. So it's periods 3 through 7. Let's do another one here. This SBR6, again, it's going to be an expanded octet. Sulfur is a period 3. So it's a period 3, which means you can use 3D electrons. So you can actually accomplish up to 18 electrons around the central atom. So sulfur is a central atom. And again, you'll have Br. So you always start off central atom, draw single bonds, and then add 6 electrons around each atom. So I guess I could move these here. So now I'm going to go and count how many electrons or valence electrons I have. So sulfur has 6. It's a group 6A. Bromine are the halogens. So these have 7. And there's 6 of these. So 6 times 7 electrons. Again, these are bromine. So I have 48 electrons. That's count how many I've used. So I got 1, 2, 3, 4, 5, 6. I got 6 bonds. Each one has 2 electrons. So that's 12 electrons. So, okay. Got 36 electrons left. I got 6, 12, 18, 24, 30, 36. So I've used up all my electrons. The bromines are satisfied. They all have 8 electrons. The sulfur has 6 bonds, has 2 electrons, so 12 electrons. So it has this expanded octet. And then you're set. Let's just do one more with the expanded octet. This right here will be an octahedral, OH. So if you have a central atom plus 6 bonds, that's going to be octahedral. So let's just do one more. Let's do I3 negative. So in this case, iodine has to be the central, right? It's the only one there, all 3 iodines. So start off like this. Draw 6 electrons around each iodine, except for the central one. Let's go now and count up the number of valence electrons I have. So I have 3 iodines. Each one has 7. So these are iodines. So it's 21 electrons. Plus I have a -1 charge, so I add 1 to it. So plus 1 electron, so it's 22 electrons I have to work with. So let's count up how many I've used up so far. So I have 2 bonds. 1, 2, so 2 times 2 electrons. Again, we're subtracting this. 4. So I've used up 4 electrons. I got 18 electrons. Now I'm going to count the non-bonding pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So minus 12. So I have 6 electrons left. Let's go ahead. Let's put those on the central atom. I'm going to kind of erase this just to make it clear. So 1, 2, 3, 4, 5. As long as there's 3 pairs around it. So now I've used up all my electrons. Now let's label these. Let's call these 1, 2, and 3. So the first and 3 electrons are the terminal ones. These all have 8 electrons. So that's set. So basically you set up so the terminal ones have 8 to begin with. Let's look at the central atom. So iodine 2. It has 2 bonds. That's going to be 4 electrons. So 2 times 2 electrons. And then plus 6 non-bond electrons. So 6 electrons. So that's going to be 10 electrons. So it's an expanded octet. Iodine is going to be period 5, I think. Yeah, it's period 5. It can use those d electrons. It can be an expanded octet. So again, this video shows you can have electron deficient for boron, and then you can have expanded octets now, anywhere from period 3 to period 7. And then the shape now, if you look at that sheet, again, I made a video on this sheet. If you look at that sheet, it's down the bottom. You have 2 bonds and then 3 electron pairs around it. That's going to be a linear shape. And this will be nonpolar, by the way. If they're all the same, it's going to be nonpolar.